Hey guys, the start of another chapter here then. So this time we're going to be looking at differentiation. Now, differentiation is part of a very powerful and important branch of maths called calculus. The other part of calculus is integration. So before we look at that, we've got the differentiation. So two mathematicians very famously developed calculus. One of them was called Gottfried Leibniz, and the other was our boy Isaac Newton. So he very famously didn't have the maths that he needed to develop his laws of planetary motion. So he invented it, which I always think is pretty cool. So in this video, we're going to go over a brief overview of what we're going to be doing in this chapter and what differentiation is. Okay, so what is it, first of all then? So differentiation is an algebraic method that allows us to find the gradient of a curve. Now, remember back in GCSE, in exams, you might have come across questions with curves and you were asked to find the rate of change at a certain point. Now to do that, we drew tangents and then worked out the gradient of the tangent. Gradient is rate of change. So what we're doing when we differentiate, we are finding what we call a gradient function or derivative of the curve function. Now what this allows us to do, it allows us to find the numeric gradient at any point on the curve. All we do then is substitute in the x value at that point into our derivative or gradient function. It also allows us to find the equations of tangents a lot easier, and it also allows us to find stationary points, which are points on a curve where the gradient is 0. Now we can also differentiate again to then work out if those points are maximums or minimums at these stationary points. So it's quite powerful, has a lot of real life applications. So if we had y equal to some function x, then our derivative or our gradient function, so let's just call it derivative for now. The derivative we write as dy over dx. Now, if this looks familiar at all, you may have watched some of my straight line equation videos, maybe on gradient, where I recommended you think of gradient as the difference in y divided by the difference in x. It's exactly the same here. Okay, then our second derivative, so if we were to differentiate again, we write as d squared y over dx squared. So that's some notation we're going to see. There is also some alternate notation where we could either say we're being lazy or efficient. Dy over dx we could write as y dashed of x, and for the second derivative, d squared y by dx squared, we can write that as y dash dash of x. So it's a lot quicker than writing dy over dx every single time. Okay, so before we meet nice differentiation, we now need to know how to differentiate from first principles, which I actually think is quite nice. It's nice to know where these things come from, instead of just doing them without a reason behind it. So, when we're differentiating from first principles, we're going to meet this thing called a limit, and we're going to meet this guy. This is basically the formula for differentiation from first principles. Don't worry about it too much now though, it's not as bad as it looks. Okay, so once that's behind us, now that is probably the trickiest thing in this chapter, first principles, then we're going to look at nice differentiation of functions. So, if we have an expression y equals x to the power n, then the differential, or the dy by dx, is equal to n times x to the n minus 1. So all that happens here, the power goes down in front of the function, multiplies it, and then the power goes down by 1. So we're going to be using that on single terms, functions, and then we're also going to use differentiation to find tangent equations and also what are called normals. Now a normal is a perpendicular line to a tangent. Okay, so once we know how to find tangents and normals, we're then going to be looking at stationary points. Stationary points are points on a curve where the gradient is equal to 0. So now that we know how to differentiate, or we will do when we get here, when we know how to differentiate to find the gradient function, we can then set that equal to 0 and then solve to find the x values of any stationary points, which is really handy. Remember when we were sketching cubics and we were finding sometimes the stationary points, we could only really find those if they were on the axes. Now that we know how to differentiate, we are able to find stationary points that are anywhere in the x, y plane. So it's quite powerful. Then what we can do, we can use second order differentiation. So we just differentiate our gradient function. We can use that to then classify these stationary points as either maximums or minimums. So it's getting more and more powerful as we go. Okay, then we're going to take a look at classifying and sketching functions. So we can classify functions as either increasing or decreasing. Not going to go into too much detail here. Differentiation is going to help us with that. And as I mentioned on the previous page, it helps us to find stationary points that otherwise we wouldn't be able to find. So we're going to be able to sketch more complicated graphs. And it's also going to help us sketching the type of graphs we've already done so far, because we'll be able to differentiate to find these important points. So for example, with a quadratic at the moment, to find either the maximum or the minimum, we have needed to complete the square. And with differentiation, we have a different approach. Okay, now once we've learned all of that, we're then going to look at real life problems. There wouldn't be much point learning all of this if we can learn real life applications. So calculus is very powerful in the science, economics, engineering. So we'll be looking at problems like areas, volumes, things like that. It's going to be fun. So lots to do. Better crack on. Take it easy, guys.